Welcome to 5.4 exponential functions. So we're going to look at e to the x, and we're going to talk about taking the derivative of e to the x today, and we'll look at into integrating as well. So some pre-calc review, all right? So we're going to quickly go through, solve these, and then graph the final part C. So in part A, if we're solving this exponential equation, we're going to first isolate the e to the negative 2x plus 8. So all I did here was I cross multiplied, okay? And, well, sorry, I didn't cross multiply. I multiplied both sides by our denominator and divided it by 4, okay? And then subtracted 1. And then we're going to convert it to log form. So natural log of 1/4 is equal to negative 2x plus 8. And to get x by itself, we're going to subtract 8 and divide by negative 2. Throwing this onto our calculator, we get our answer. Looking at part B, now we've got a log equation. So remember, natural log is really log base e. So we could say e to the second equals our argument, the square root of x minus 3. Getting our getting rid of that square root, we're going to square both sides, and that's where we get e to the 4th equals x minus 3. And then to get x by itself, we simply add 3. Throw it onto the calculator, and we get our answer. And then finally graphing, okay, just plotting some points. So I plotted the point when x is 2, because that gives us a nice point of e to the 0, which is simply 1. And then we can choose some other values, and we get our graph. We've got this asymptote at y equals 0, right? This will never equal 0. It'll get close, but this alone will never equal 0. Okay, now we're going to get into some rules dealing with e to the x. So if we want to take the derivative of e to the x, we're simply left with e to the x. That's the nice thing, okay? Now if we have e to some other function that's not in terms of just x, or it's in terms of x, but more of a function there, we just have to remember our chain rule, okay? If we're integrating, that means the integral of e to the x is simply e to the x plus c. If we have e to the u, then we're going to do that u substitution and then make our substitution back and go from there. Okay, so if we go through our first example here and we want to find the derivative of x squared times e to the negative x, well, this is just a product rule, so we got to remember that. So the derivative of x squared is 2x. We leave that guy e to the negative x plus, now we take or keep x squared and take the derivative of e to the negative x. So that's e to the negative x, and then the chain rule is where we get that negative out front. So now if we kind of cleaned it up, we would get our answer of y prime is equal to 2x minus x squared over e to the x. This next example wants us to find the equation of the tangent line at negative 2, 4 for our equation y equals ln of e to the x squared. So one thing we can think about is we need the derivative, right? So if we take the derivative of the natural log of e to the x squared, remember the derivative of natural log is 1 over that argument, and then we have to use the chain rule. So the derivative of e to the x squared is just e to the x squared, and then we need the chain rule for this x squared portion, so times 2x. So what we should notice is the e to the x squareds cancel, and we're simply left with y prime is equal to 2x. Now, one thing we could have noted from the very beginning is that we could use our log properties here and move this exponential power in front. So we get y equals x squared times the natural log of e, and hopefully we remember that the natural log of e is simply 1. So what we could really do is say, oh, well, y is really just equal to x squared. So then when we take the derivative of it, boom, we're back to y prime equals 2x. So it's something, if you recognize it, then you don't necessarily have to worry about that chain rule. Anyways, continuing on, now we have to evaluate our derivative, right, because this represents the slope of our tangent line at the point negative 2, 4. So we'll plug negative 2 into our derivative, and we get -4. So here's the slope of our tangent line at that point, and now we can go ahead and write the equation of that tangent line. The slope is -4, and it passes through the point -2, 4. So there we have it. This next example, now we're going to integrate using e to the x. Well, in this case, I see multiple e's, and the best thing to do is let's try to use substitution. So if we let u be the denominator, so 1 plus e to the 2x, then the derivative of this is just going to be e to the 2x and then that chain rule times 2. So that takes care of the numerator portion, right? So we'll take care of that portion with our du, and we'll have to throw a 1/2 out front, right? So as we go through, we've got 1/2 times the integral of 1 over u du. Integrating 1 over u, we know that's the natural log of the absolute value of u, all right, plus c. And now we have to make our u substitution back in terms of x. So we get 1/2 times the natural log of the absolute value of 1 plus e to the 2x plus c. Now, one thing to note is that this portion will never be negative, so we can essentially drop the absolute value bars. So either one is acceptable, but you'll probably see it more written like the second version here without the absolute value, again, because that 1 plus e to the 2x, that can never be negative, okay? This last example is just getting us back into talking about extrema and points of inflection. So if we're given our function f of x equals x squared times e to the -x, that was from our first example on the front of our notes, then if we want to find our relative extrema, we know we've got to go and find our critical numbers. So we already found the derivative in that previous example, all right? And one thing to note here is when we're trying to find our critical numbers, remember we set it equal to 0, or it's when f prime doesn't exist. Well, this will never equal 0. Okay, e to the x will never equal 0, so we really just need to focus on when this function equals 0. So just focusing on that numerator. So we set that numerator equal to 0 to get our critical numbers, and we get 2 critical numbers. Using that first derivative test, setting that up and using our number line, during this interval when x is less than 0, f prime is negative, between 0 and 2 we're positive, and back to negative after 2. So f goes from decreasing to increasing at 0, so we have a relative minimum, and increasing to decreasing at x equals 2, so that's where we have a relative maximum, and we'll make the conclusion in the end. But now we need to find points of inflection, so what do we need to do there? Hopefully we remember, we have to find that second derivative. So as we go through, now taking the second derivative, maybe it helps to show the first derivative, we're using that quotient rule. So low d high minus high d low all over low low, or whatever song you guys learned. Okay, so the derivative of the numerator is 2 minus 2x times our denominator, e to the x, minus our numerator times the derivative of e to the x, which is just e to the x. So what we should notice is all three of these terms have an e to the x in them, so we can kind of cancel those. And then we're down to this right here. All right, and then gathering our like terms, we get our second derivative to be x squared minus 4x plus 2 all over e to the x. So again, our denominator will never be 0. Okay, so we're really just focusing on our numerator, setting equal to 0 to get our possible points of inflection. And so we get 2 possible points of inflection, 2 plus root 2 and 2 minus root 2. And now we get to our concavity test. Okay, remember it's not the second derivative test, it's the concavity test. All right, so we're going to figure out 2 minus root 2 is about 0.59 and 2 plus root 2 is about 3.4. F double prime is going to be positive in this interval, negative here and positive to the right. So when f double prime is positive, f is concave up. Negative, we're concave down. Back to positive, we're concave up. So we do have a point of inflection at this x value and a point of inflection at this x value, since we go from concave up to concave down and concave down to concave up, or f double prime changes sign, goes from positive to negative, negative to positive. so we can go ahead and make our conclusion. Okay, so by the first derivative test, since f is decreasing then increasing at x equals 0, we have a relative minimum of 0 at that point, 0, 0. And since f goes from increasing to decreasing at x equals 2, we've got a relative maximum of 4 over e squared at that point. And by the concavity test, we know we have our points of inflection because f double prime goes from positive to negative and negative to positive. If you have questions, let me know.